Hi, EP Physics. Today we are going to be learning how to calculate the moment of inertia of a disk or of a circle. Disk is going to be more physically relevant for us. So in my image here, I have our capital M that represents the total mass, and then the capital R represents the total radius. Lowercase r is going to represent the different radii, and our small little area there is going to have the different little masses. So the first thing that we should do is we should start by writing out our integral for inertia. So inertia is equal to the integral of radius squared multiplied by our small little masses found at those radii. Now, when I am working on this, I'm going to be finding the small, oh, that was a horrible circle. Let's go back here. Let's try it again. That's a little better. I'm going to be finding the small masses found in our rings here. So here we have a small dr because what we want to do is we want to find dm in terms of radii, right? If I do r squared dm, right, I'm just going to end up with mr squared, but that's not how where all the masses are located, right? They're not all found at the edge of the radii. Some mass is going to be found closer in, some mass is going to be farther out. So my dm here is going to be equal to the density, rho, multiplied by the small area we find at um, at these different radii. So I want to also represent our area in terms of these small radii. So the first thing is I'm going to be at a radius, and that is going to get us a circumference of 2 pi r. And then I multiply by my small little radius that makes up the area. And so this will get me the area of that ring is the 2 pi r, so that's that circumference again multiplied by my tiny radius. And so now I can substitute this back in to my equation. So I get the integral of radius squared, and then I have rho 2 pi r dr. Now, something that we should include here is we want to place our bounds because we have clear bounds, and that is the radius at 0 to a radius all the way at capital R, right? We're not going to go out infinitely, we're only going to go to capital R. So let's pull out all of our constants. So that's going to be 2 pi, and it's going to be our rho here. And then we're left inside from r equals 0 to r equals r cubed, right? R squared multiplied by that radius, and it is integrated with respect to radius. So we finish this out, and we get 2 pi rho r to the fourth, right? We had r cubed, and we divide by and we divide by 4. So these should cancel out, right? Leaving us with 2. So far we have the inertia is equal to pi rho, and actually that should be a capital R. Let's go back here. Let's make that a capital R, right? Capital R to the fourth divided by 2. Now, our density, let's say it's evenly distributed. So density, will go all the way over to the right side here, is equal to the total mass over the area of our disk, right? If the mass is evenly distributed, then all the little bits of mass are going to be located in evenly throughout that area, right? Since density is the amount of mass per area here, or if we had it linearly or in terms of a volume, right, we would just substitute that in instead. So we're going to plug this into our equation, but first we have to figure out what the area of our disk is. So mass stays the same, but the area of a disk, or a circle, is equal to pi r squared. So we plug this back in and we get mass and r to the fourth. Move that pi over, divided by 2 pi r squared. Well, our pi's cancel. And the radii at the bottom, or the radius at the bottom, cancels fully, and we're left with 2 on top. So, finishing this out, we have 1/2 the total mass multiplied by the total radius squared. And so this is how you integrate for a disk.